Hey guys, and welcome back. If we recall, data is one of the fundamental pillars of asset management. In the quest to make sound asset management decisions, best practice organizations have placed an emphasis on data or information to support those decisions. Data itself can and should be treated like an asset, as data can provide our organizations nearly unlimited value in supporting decisions, communicating risk to stakeholders, or understanding how assets function for those that use them. Engineers have long valued hard work, but not until recently have we begun to value data, as we do not see the work that goes into collecting and maintaining data as directly supporting the mission. But this work is not for nothing. Data is the backbone of our asset management system. Sometimes it feels like we suffer from information overload, data glut, like there is more data out there than we can possibly use. Sometimes it feels as though we collect data and store it just for the sake of doing it. In the context of asset management, data is the fuel that drives our decisions. If you recall how we defined an asset in our earlier lesson on asset management principles, it is something that can provide tangible or intangible value to an organization. To the pilot, an airfield is an incredibly important asset. For engineers, that asset is the data we need to drive decisions. In this lesson, we'll discuss data and data analysis as it pertains to asset management. By the end, you should have a good understanding of where data fits into the overall big picture. We will explore two types of data and how they can be used to inform asset management decisions. We will also explore a simple data analysis process which can be applied both in our daily lives and in the context of asset management decisions. While we cannot make you an expert in statistical analysis, we'll start with an overarching picture of data some tips and tricks along the way for looking at data to try to make sense of it all. We'll then explore ways in which we can extract value from our data and begin to look at those two types of data which have two different requirements for us. Finally, we'll use lessons learned from the geospatial analysis field to uncover a 7-step process if we look at program analyze data and inform decisions document that transformed our CE enterprise. The role of the activity manager or portfolio manager involves looking at data. You can see here it says responsible for data related to and management recommendations for a system or systems at the base level. Part of that task involves conducting regular quality assurance reviews of data to ensure accuracy, ensuring the data remains current and updated and reflects a true picture of the current status and health of the covered systems of that portfolio manager. So you can see that the portfolio manager cannot do their job without data. And I would argue that if you are in the R&O section and you are in customer service, or you're one of the sub-ant managers, or you are an ops manager, you can't necessarily do your job without data either. In one of our previous lessons, we talked about measures of performance, sort of benchmarks for us to make decisions. Well, where do those measures of performance come from? Where does the information come from to support them? Well, it's data. It's data that we need to make our decisions. So if the performance measures are the basis for the decision that we make, the data is the foundation upon which that basis rests on. Another place we can look to see how important data is in the 2016 Civil Engineer Flight Plan. The Civil Engineer Flight Plan was put together by the Headquarters Air Force A4C team back in 2016, and it sort of paves the way for the way engineers need to think and act in the next 20 years. It outlines two end states, and I've given you one of those end states here. Provide resilient and right-sized installations with agile engineer capabilities to meet Air Force missions. To get to that end state, there's several lines of effort, but the one that I want to put in front of you today is line of effort 2.1. Optimize installation operations and footprint. It's kind of obvious to me, and hopefully it's sort of obvious to you, that we can't optimize anything without information on which to optimize. Information is data. So I've taken a quote and put it in front of you down below there. Enable facility data to become targeted, auditable, and of predictive decision quality to inform and support strategic investments and real property portfolio management and accountability. So what does that actually mean? Well, it means we got to start collecting information that can help us predict as opposed to react. It has to help us tie our assets to the missions that support them, and that information is going to come from you, the person who's taking this course, the R&O technician, the customer service representative, the AMP or sub-AMP manager. We have to take this information about our facilities and let it go to work for us, as opposed to us working for the information. So let's start at the very beginning. I want to define a couple terms for you before we move on. Let's start by defining a datum. A datum is a piece of information, either an assumption or in precise form, from which inferences may be drawn. Data, or the plural form of datum, is a collection of information known or assumed as facts, making the basis of reasoning or calculation. Data is vital to us as engineers. It provides us with boundless potential to innovate solutions to the problems with our built environment. Think of it like this. Data is the soil upon which we can grow sound asset management decisions. It's amazing what data can tell us. It might tell us how old something is. It might tell us what color something is painted, or where it's located. In this context, data is a representation of the world around us. In an ideal world, the representation would be identical to the facts, but sometimes that is not the case. For a moment, think about what it means to have reliable data. Data is assumed to be a fact. Therefore, if we can prove that the data is false, we have bad data. One of the most difficult tasks for engineers today is ensuring data is accurate and accurately represents our built environment. To the best of our ability, we want to ensure data tells the truth. If we use this data to inform decisions and it's inaccurate, we have used bad data to make a bad decision. Let's define two different types of data which are equally useful to asset managers. The only thing that separates these two categories is time. Our first type is persistent data. Persistent data is information that is unlikely to be modified and will not change with time. Examples of persistent data include square footage, construction or installation year, or real property unique identifier. Persistent data may be changed, for example, if we add square footage to a facility, but we can expect it to remain the same for our analysis' sake. The second kind of data is dynamic data. Dynamic data is information which can and will change over time. A good example of dynamic data is condition index. The condition index datum is a representation of the physical condition of our assets and is a function of age. So, as the assets age, we can expect the condition index to decline. Some data will change rapidly, while some may not change much. It's important to know how much the data can change from asset to asset or from year to year. This will guide how we maintain the data to ensure what we analyze accurately depicts the real world. No matter what kind of data we're talking about, it should provide an accurate representation of the physical world. And the cost of collection and maintenance should be proportional to the size and scale of the decisions being made using it. Asset managers must use both persistent and dynamic data to inform asset investment decisions. As we saw in the performance measures lesson, we can use condition index to measure the reliability of an asset. The condition index itself is a piece of dynamic data. When we combine that with the persistent data point of construction year, we can see how our assets are aging. By knowing how fast these assets degrade, we can get ahead of repairs and replacements before they deteriorate to the point of no return or cause an emergency service call. Similarly, we could use facility number and a ratio of corrective maintenance to square footage to measure how expensive a sample set of facilities is to maintain. As we can see, for asset managers, the power resides in how we use the data to inform decisions or recommendations on how best to manage our built environment. For us, data is the asset as much as a facility is to a services airman. Recall for a moment the definition of an asset. An asset is a thing, item, or entity that has potential or actual value to an organization. Asset management is the process by which an organization extracts value from its assets. Now what happens if we change the word asset to data? Let's take a look. We can see that we must treat our data just like we treat our assets. Data management is the process by which an organization extracts value from its data. So, how do we extract value from data? Sometimes the sheer quantity of data is utterly paralyzing. Sometimes it feels like we collect data just for the sake of collecting it. So how do we know if we're collecting the right data? The answer lies in something most people use every single day to inform decisions about their own lives: Geographic Information Systems, or GIS. A geographic information system is a tool which allows us to visualize data on a map to inform decisions. I've gone ahead and defined it for you for reference, but believe me, you already use GISs every day. Ever used the Maps function on your smartphone to find a friend's house? You've used GIS. Ever used an app to decide what restaurant to eat dinner at? You've used a GIS there too. GISs combine spatial attributes, or something's location, with any number of other attributes which help decision makers arrive at a data-driven decision. Ever decide to go somewhere for dinner based on the average review score on Yelp? You made a data-driven decision. The process to arrive at that decision in the realm of geographic information systems provides us a very useful model to use in asset management. Let's take a look at what it looks like. The GIS analysis process is 7 steps and seeks to answer questions and solve problems in the real world. It all starts with defining the problem and concludes with presenting the results. Let's take a look at each of these steps and how they apply to both decisions we make every day, particularly getting dinner, and some of the problems we face in the world of asset management. The first step of the process is to define the problem. What am I trying to do? This is the single most important step of the process. Get this wrong, and you'll end up finding the correct answer to the wrong question. Ultimately, our analysis should do one of 2 things: either support a decision or recommendation, or confirm or denounce a bias. An example decision many of us are faced with every day is the decision of where to eat dinner. It's a decision literally every single one of you make every single day. So we'll use this as an example moving forward in our personal lives. But what about in the context of asset management? Well, an example problem asset managers might be trying to solve using this process is this one. Which assets are most likely to cause emergency service calls? If we are going to analyze data to make a decision or provide a recommendation, we must start with a problem statement. The second step of the process is to define the criteria we will use to evaluate the problem or make a recommendation. Let's tie this back to our lesson on performance measurement. Look familiar? Recall that we use performance measures to influence decisions. Often we will decide to measure something which drives data requirements. These 2 processes are inextricably linked. It's important to note that not all criteria are measures of performance, but very frequently, measures of performance are criteria. In our personal life example, we decide that our decision to eat dinner will be influenced by where it is, by how popular it is, and how much it costs. We might have a maximum distance in mind, a low threshold for popularity, and a cap on price, but these are what we decide. In our asset management problem, we decide that we will use these 2 criteria to determine the likelihood of an emergency service call. Now you see we've taken one of the dimensions of performance measurement and linked up a more ambiguous criteria, physical attributes. In either case, these criteria will drive the next step of the process. In our third step, we must use the criteria to define the data requirements of your analysis. You will either already have it in one place, have it in multiple places, or you'll have to go and collect it. As an example, you might have the facility number in your sustainment management system, and you might also have some figures on corrective maintenance and TRIRIGA associated with that facility, but you may not have the condition index just yet. So you have to go and do a condition assessment of that facility to get a reliable condition index value. In our dinner example, we use the data point which represents our location compared to the location of the restaurant in miles, the average customer rating in number of stars, and finally, the average cost of a menu item. For our asset management example, we use the facility number to denote location and the square footage to denote size. Condition index and corrective maintenance are used to denote reliability. Step 4 is deceptively important because it forces us to think about how sensitive our data set is to outside factors like variability and subjectivity and maybe some other factors which could ultimately impact the result. In this step, we want to think back to the problem we're trying to solve and compare that to the data we will collect to prepare us for the next step of analysis. This is our warm-up before the big game. Think of the sensitivities in both of our examples thus far. For our popularity criteria, how sensitive is that figure to someone having a bad day? What if one customer put a bad review on an otherwise brilliant restaurant, which brought the score of that criteria down? Similarly, in our asset management example, how is our corrective maintenance data affected if we've been categorizing enhancement work as corrective maintenance all along? It's important in this step to know what could impact the results of your analysis. The other portion of this step is to plan the steps of collection and analysis. So where's your data coming from? Who owns the data? In our Yelp example, it's simple. Open the app, enter the criteria, hit search, and you're done. In our asset management example, we'll be pulling data from several locations and pulling several reports to arrive at something that we can analyze. In step 5, we want to get our data ready to analyze. Make it easy on yourself. Assuming we have the data set in raw form, we want to remove or hide information that would otherwise distract us from solving our original problem. In our Yelp example, it's done for you in the background of the app. In our asset management example, we're pulling raw data from both Builder SMS and Tririga. I might have tens of thousands of rows in a data set. So much like cooking, we will trim the fat before we cook. We'll trim and filter our data set down to something that is analyzable. When I say trimming, I mean removing columns that you don't need. Typically, these columns contain row after row of the exact same value. Filtering removes specific categories of rows from your data set. Think of it like cutting sheets on a paper to make it smaller. Trimming is cutting vertically to make the sheet thinner. Filtering is cutting horizontally to make it shorter. In this example, I've downloaded a raw Builder report into Microsoft Excel and justified it to full screen. That's a lot of data. I'm sure you can't see all the detail in it, but you might be able to see several instances where there seems to be a lot of rows with the same information in them. Let's get rid of those columns. Now, once I've removed them, you can see that our data set is a lot thinner than it used to be. We can start to read what's in each cell. We're getting there. Let's take it one step further and filter out some of those rows. When you filter out rows, you will want to highlight the entire header row. Select the Data tab and click Filter. Once you've done that, you can see little arrows appear at each of the header cells. Now I can shorten my data set by getting rid of categories I don't need to be looking at. In this example, I only want to look at facilities measured in square feet. We could apply this technique to any of the header cells to filter out any data that's in our way and make our data set shorter. Once my preparation is done, it's time to go to work. Now, step 6 is also deceptive. It looks so easy on paper. I assure you, it is not easy, and it requires lots of practice to become proficient. The first thing I personally like to do with any trimmed and filtered data set is to sort by various fields to see what jumps out at me. I'm looking for any abnormalities that stick out. Really low condition indices, really high square footages. Each of these lists represents a list of mosts. The most bad facilities sorted by BCI, lowest to highest. The most big facilities sorted by size, largest to smallest. Once I've sorted the data set, it's helpful to perform descriptive statistics on a number of series to learn more about what constitutes an abnormality. If you're curious how to perform descriptive statistics, click the hyperlink to take a micro lesson on performing descriptive statistics in Microsoft Excel and what some of those statistics actually mean. In the third portion of this step, I want to ultimately find any abnormalities of my data set. That's most frequently where answers to questions lie. In our Yelp example, It's easy. Once I hit search, I can just choose what restaurant I like the most based on the criteria I chose. In our asset management example, we pull together our data, sort it, and see what the story tells us. This is a simplified data set from earlier. I've gone through the trouble of pulling some Tririga data for each facility and placed it next to the BCI column. The column on the right is where we execute a calculation of corrective maintenance divided by square footage. Sorting this field tells me how maintenance intensive each facility is. Now compare that to the BCI. See any correlation? It might not be easy to see this in the data set, and that's where step 7 comes in. Step 7 is for the artists. The art of analysis is visualization. In this step, we use the data we have to tell a story. Hopefully that story is the solution to the problem we started in step 1. No matter what, we want to keep our visuals simple and legible, and our visualizations should answer more questions than they generate. Finally, labels are essential. It's kind of amazing what a little visualization can do to some data. For our Yelp example, the user interface allows me to see the criteria I set and make a simple decision using enormous amounts of data in the background. For our asset management data set, let's take a look at the correlation I mentioned before. We now know where it is most likely to generate a service call, and we have both a lagging indicator of corrective maintenance per square foot and a leading indicator of BCI telling us that. In this instance, the answer to the question often begs another question. What is the next step? That is what optimization is all about. In this specific example, I'd be curious what systems show a sign of failure, and I'd love to see what a project would look like to renovate that facility. I bet it would be a great candidate for a repair project. So there we have it. The 7-step GIS data analysis process applied to both our everyday lives and a real-world asset management problem. Remember the fundamentals of each step. And don't forget that the most important step is the first one. Once we define a problem or measure of performance, we define the criteria, which define our data requirements. Before we begin analyzing, we must assess how sensitive our data set is and plan the analysis. To make things easy on yourself, don't look at the data you don't need to do the analysis. In the actual analysis step, statistics help us understand the characteristics of our data set, and arriving at something that looks coherent does take a lot of practice. Finally, step 7 is where we take zeros and ones and turn them into something meaningful, which can influence the way we maintain our base, or it can mean the difference between receiving funding for a project or not. Or, alternatively, it can help us decide where to eat. That's what I love about this process. It's elegantly simple and applicable to just about any decision that we make. In this lesson, we discussed the importance of data in asset management. Engineers have long valued hard work, but the time is now for us to start placing value in our data. It contains so much potential. As I said earlier, it is the soil of our decisions. We must now shift our focus to how we can best extract value from the vast quantities of data that we have. For us, that means making sure the data is accurate and is a true representation of the physical world. It's important to note, as well, that as we collect all of this data in various forms for our own use, there are others out there using this data to inform Air Force-wide decisions on our behalf. So it's imperative we remember the importance of having accurate data. Next, don't forget that there are fundamentally 2 kinds of data. We call them persistent and dynamic data. The only difference between these 2 types is whether or not they change with time. Finally, we discussed the 7-step GIS data analysis process as a model for us to use when informing asset management decisions or where to get some dinner. Hopefully you've enjoyed this foray into the world of big data and data analysis.